everyone. Today we're going to be talking about rootkits in 64-bit Windows operating system. We already talked a lot before in the prior episodes, which you can easily look up in a playlist about user mode rootkits, kernel mode rootkits in 32-bit, and how kernel rootkit perform loading. So in general, if we kind of simplify, right, what rootkit needs to do, it needs to load, and then it needs to usually hook to perform hiding, right? Hook and hide, to hide itself and hide other malware pieces executing. And as you learn from our discussion about 32-bit Windows, 32-bit Windows kernel was a complete Wild West that would allow hooking, modification, there were no protection, and loading was very easy as well. Both of these things are very easy in 32-bit. You could load driver directly, you can create a service, you could patch actual existing driver on the disk, and that would actually load your rootkit driver. So in 32-bit operating system, both of this was very easy for malware and it was real Wild West in the kernel. So at some point in 64-bit version of this kernel, Microsoft said enough is enough. And then introduced two mitigation techniques. One is only load sign driver, so it's a sign check. So in 64-bit operating systems, you can only load the driver if it's assigned by Microsoft. If your driver is not signed, it's not going to be loaded. And as well as all Windows drivers and kernel would be signed as well. So if you modify a driver on the disk, the signature check would not pass, it would not work, right? So that made it harder to load a driver there. And then the second thing would be a patch guard, or KPP, kernel protection, or simply patch. And what patch guard would do, it would guard SSDT, our service descriptor table, like system service descriptor table, IDT, interrupt descriptor table, and I believe GDT. That would be a global descriptor table. Interrupt and system. That made the rootkit lives much harder, because now not only you somehow needed to sign your driver, which is very difficult, complicated process, because now Microsoft would actually verify a driver source code before signing it, meaning it would not sign a simple rootkit. In general, there were cases when it did, but also, even if you load your driver, you cannot actually use those very common techniques of patching system tables, or as well, it of course protected NT-OS kernel itself, right? And it also stopped exporting SSDT pointers, so it actually was even hard to find system services dispatch table. So that made rootkit lives much harder on 64-bit. So what do you say? Does it mean that 64-bit Windows operating system didn't have rootkits? Of course not. So let's have a look how exactly rootkits were bypassing these new two mitigations in Windows. So we have these two technologies, right? So how malware would bypass it. So let's first talk about sign check. Of course, even though Microsoft would require the signature check, it cannot require it in every single use case, because when you're a driver developer and you're just developing a driver, of course you need to debug it. And to debug it, you need to use Windows, and you of course need to use 64-bit version of Windows, and you need a way to actually be able to compile and run and debug, compile, run, debug, and you cannot wait for Microsoft to check every single debug version you want to test. So that's why, of course, Microsoft introduced special mode, which we'll call testing on. It's a modification of BCD edit settings, which if set, it would disable, after reboot, it would disable the patch guard. Another option would be no integrity checks. pretty much does very similar thing. I believe that also will disable patch guard. Both of them, I think, will disable patch guard. And there's another option which is called debug on, and that is designed to run a kernel debugger. Of course, if you run a kernel debugger, you cannot run a patch guard, and you should disable a bunch of checks inside. So that would actually disable the patch guard. So we can move it here. And it has some checks that actually debugger connected, but malware could manipulate some structures to make system believe that debugger is on, and that would run without patch guard and without the sign check. And by the way, all of them would also disable KPP. So those options, if malware set the BCD edit, that would need the admin credentials for that. But if malware sets BCD edit and then reboots the system, it could load rootkit inside, at least for this specific run, because the sign check would be disabled. So that would be one very kind of simple way to do it. There would be others. For example, it could exploit either Windows driver or third-party driver. And while Windows driver, Microsoft might pay more attention to security and they might be pretty good, even though I have to say this win32k.sys, which is a graphical subsystem driver, was full of bugs and was one of the major holes in Windows, especially when we talk about period 2005, 2010. That would be absolute nightmare in terms of exploits. So that would be one way to get in and be loaded, right? You execute an exploit inside. Or third-party drivers, right? Sometimes, and that's even popular nowadays, but it started back in 2005, 2010, that when you have a signed but vulnerable driver, which allows you execution of any code inside kernel, you can actually bring it with you as a part of your malware, even though it's a benign driver, load it because it's signed, it passes its side check, and then exploit the vulnerability inside of it. It's very easy, and the problem is, even if everyone knows that that is a vulnerable driver, people would use it. So Microsoft cannot just ban a vulnerable driver because people might have it installed. So it would kind of create these holes inside of the sign check and allow malware to execute exploit and execute malicious code inside. There are other problems as well, how the sign check can be bypassed. And specifically, it's a boot process compromise. And even more specifically, it would be MBR, master boot record, and I believe VBR, virtual boot record, volume boot record. Malware could modify this too, and that would of course becomes the bootkit. We're going to have a separate episode about the bootkits, so I'm not going to cover it now, but if those other approaches fail, malware actors could use the bootkit and create a bootkit which pretty much bypass it. The bootkit usually loads in the bootkit process before Windows, and it can disable sign check. It can also even disable patch guard before everything is executed and get the full control over the system. Besides those ways to bypass sign check and KPP, there were others. For example, by using an exploit, Rootkit could get write, how would they call it? The write anywhere vulnerability, right? And it could write a certain number of bytes inside the kernel memory. And so the patch guard would have, and it also can read, right? Usually it's read and write, and you can execute the command, and you can read a few bytes and write a few bytes through the vulnerable driver. So what it could do, it could find the flag which notifies KPP that it should be disabled. So for example, when you run testing on or no integrity checks, when Windows boots, it sets a certain flag which tells KPP not to be started, right? It's some Boolean variable inside the memory. So what exploit could do, it can modify that Boolean variable. First, use read functionality to read and find where this flag is stored, and then use write functionality to override it with 0. And this can just completely disable a patch guard. Another vulnerability which existed back in the day in the patch guard was to actually, when the patch guard triggers, when it detects that something was modified, what it would do blue screen of death, right, SOD, and it does it through a special function which I think we call bug check. And so this would check if there was a failure and it would crash the system. So what one could do is would try to modify the bug check itself to not do anything. So for example, if you're a rootkit, you get loaded, then after you get loaded, you have access to the bug check, you can find it in the memory and you can modify it. And then even if KPP triggers and say, hey, we need to PSOD, it just doesn't PSOD because you control the bug check. And that was another method to bypass it. So as you can see, indeed, in 64-bit version of its kernel, Microsoft stepped up and improved it drastically. And over the years after 2010, there will be more and more improvements in the patch guard. But between 2005 2010, there was this kind of first version of 64-bit, first generation of 64-bit kernel. And it included sign check, it included patch guard, and they were pretty efficient. A lot of rootkits died, like a pure rootkits died. At some point, these techniques were so noisy that every single antivirus would detect them. So they kind of died down as well. So the only real choice the rootkit would have is to really either exploit and try to disable KPP and load its code, or do a bootkit. And the bootkit is the next topic we're going to cover, but it's probably going to cover in the next time frame between 2010 to 2015, because that's where bootkits both advanced the most and died. At least in the software type of MBR, VBR rootkits died. And we're going to talk about this later. Okay, that's it about Windows rootkits 64-bit. I hope you enjoyed. Don't forget to share. Don't forget to subscribe, and don't forget to tell your friends or to your sister or your mom or your grandma about this podcast and spread the word. Thank you very much, and I see you in the next episode.